Welcome back. Today we're going to continue our discussion on colligative properties by talking about boiling point and how the boiling point of a pure substance can differ from the boiling point of a solution. Remember that boiling occurs when the vapor pressure of a solution or substance is equal to the atmospheric pressure that's pushing down on it. So it's not really about heat, it's just about when those two things are equal to each other. From Raoult's law, we know that the vapor pressure of a solvent decreases when a solute is present. Because of this, we can then also assume that the boiling point will be higher for a solution than from a pure solvent. I almost said the wrong thing. So this is actually something that we just did in the lab, and hopefully you discovered this as well. We were boiling pure water, and we were comparing it to the boiling point of salt water. Hopefully you noticed during that lab that the salt water boils at a higher temperature than the pure water does. Well, that's because the solution with the solute dissolved in it brings down the vapor pressure, which causes the boiling point to go up. We have a way to quantify this. It's an equation that looks a little like this. Delta TB equals this constant KB times our friend molality. So let's define these letters here. So that's TB. KB is a constant. We just look up KB. It's not, sometimes we solve for KB, but sometimes we just look it up. It's pretty easy to use. And then of course we have molality. And remember that molality is moles of solute divided by kilograms of solvent. Molality is different than concentration. Concentration is moles over liters. Molality is moles over kilograms. So don't make that mistake. It's important to keep that in mind. Let's explore this a little bit. So, whatever we find in this equation, let's kind of go back before we keep going. This delta TB, this isn't the new boiling point. This value that we're going to calculate is actually the change in boiling point. So the amount that we get for TB is the amount that we need to add to the boiling point. So it's actually kind of a better way to define it. Instead of saying that it's the change in the boiling point of the solution, you might instead write next to it something like, well, delta TB is actually how much the boiling point increases by, or how much it goes up. It's not really the change, because it doesn't go down, it only goes up. So it's how much it goes up by, right? Now, the vapor pressure produced by a boiling solution consists of pure solvent, but the thing that stays behind is the solute. You might have noticed this in our lab. When we were boiling our salt water, and after you were done boiling it, you might have noticed that in your beaker you had a bunch of kind of like white powder. That's the solute. The solute, which is the NaCl, stayed behind after all of the solution, or the solvent, was boiled off. So that means that the solute does not boil. It's the solvent that boils and evaporates, not the solute. That's important for the connection between these two things. We can analyze this using a graph. Let's slap down a graph here for ourselves. And this graph may be a little familiar to you. We are going to plot temperature versus time. And let's use just a color like this. Use green for the first one. Let's say that we are starting our solution, or this is going to be the pure solvent. So just solvent by itself, our pure substance. We're going to heat it, and we're going to heat it, and we're going to heat it. And you may notice or recall from the lab that while we're heating it, eventually the temperature levels out. And this makes sense to us. It kind of connects back to a previous concept, right? We know that when something is going through a phase change, the temperature does not increase anymore. So this is just the solvent by itself. When we were doing the lab, that would have been like maybe just the water, you know? So now let's say that we have the solution, which we are going to start at a different time. The rate might have been a little different, which doesn't really matter too much here. I just want to make sure that we can see the different lines. But you might notice, like I said before, that the salt water is going to boil at a different temperature. But here's something that you might not have noticed. It's not going to be just a straight line. Instead, you might notice that the temperature of the solution slowly still goes up. So this is the solution. And you might think to yourself, well, why is that? Why is it that the solvent by itself stays constant, but the solution steadily increases while it boils? Well, I want you to think about that statement that we just said previously. As the solvent boils, what's left behind? Well, the solute is left behind. So if the solvent is going down, like decreasing, but the solute is staying, wouldn't you agree then that the concentration of the solute is increasing? And as the concentration increases, the vapor pressure continues to decrease, which means that in order to continue to boil, the solution has to continue to rise higher and higher. Oh, so that might be something to keep in mind. I'm not going to write anything down here, but I really encourage you to write that connection down. Let me say it again. As the solution is boiling, the temperature continues to rise because the concentration of the solute is increasing. If the concentration of the solute increases, that means the vapor pressure continues to decrease. Therefore, the temperature has to keep rising in order to continue to boil. Make sure you remember that. It's a really good relationship to keep in mind. Let's keep going. So we're going to skip ahead of freezing point for a little while, so kind of roll through this a little bit. Here we are at the examples. Now, in your note packet, the examples are actually written out, which is great for you. For me, for some reason, again, mine are not. So let's just kind of work through these. It says compute the boiling and freezing points. We are only going to focus on the boiling points. So please ignore the freezing points for now. Don't cross them out or anything, but leave yourself a little space because later we'll come back and we'll do the freezing point problems. But right now I just want to focus on the boiling point. So we're going to compute the boiling point of 25.5 grams of 4-nitro-2-toluene sulfonic acid dihydrate. I'm just going to call it toluene sulfonic acid. So, and that is being dissolved in 1 × 10⁻² grams of H2O, which notice that it says it is a non-ionizing solute. We'll get to that. There's a difference in approach depending on something if it's an ionizing solute or a non-ionizing solute. In this case, it is non-ionizing. So, we can rely on this equation that we saw before. Now, most of the time, sorry, my molality was a little weird. Most of the time, the first step that we want to take is usually calculating molality, because Kb is something that we can just go back and look at the table. You should have seen that in your notes you had like a big block of table there. So we're going to go back and look at that in just a second. It's just a value again that we look up. So we'll practice that in a second. But let's calculate molality first. So we have to first determine what's the solute and what's the solvent. The water is probably going to be the solvent for most cases, and it also says that it's toluene sulfonic acid in water. So that means that the toluene sulfonic acid is the thing being dissolved, the water is the solvent. So we want to first start, remember that molality, just to keep your head on straight, that's moles of solute divided by kilograms of solvent. So you want to start there. We want to first get our grams of solute into moles of solute. So that's going to be 25.5. Ooh, my 5 got a little weird there. 25.5 grams. I'm not going to write the formula because it's kind of long. Hopefully you don't mind. And the molar mass for this is 253 grams. But you knew that, of course. Now, when we punch this up, we get 0.101 moles. So we are going to now divide that by kilograms of solvent. Be careful, not grams. It gives us grams. So we have to convert that into kilograms. So that's just 0.1 kilograms of solvent, which means our molality is 1.01. Now that we know our molality, we can plug it into the equation. So we multiply our molality. Let's go look for the Kb first. This is for water, so we're looking for the Kb of water. That is 0.515. So we take that 0.515, and that's Celsius per molal, and we multiply it by the molality. And when we do that, that's going to give us delta Tb. Now, this 5.20 that it gives us is not the answer. It's like I said before. And it doesn't really make sense for it to be the answer. We're trying to calculate the new boiling point of water. How does water go from 100 degrees Celsius to 0.520 degrees Celsius? That doesn't make any sense. This is how much it increases by. So that means we have to take the original boiling point of water. We want to bring it out to the appropriate number of sig figs. And we add it to the original boiling point of water. And now, this is our answer. The question was, what's the new boiling point? That's the new boiling point, not the other thing. We add it. Boiling point elevation means go up. We add it. Okay? Why don't you try the next one on your own? It says compute the boiling, or just boiling point again, of 100 grams, I should just say, of, oh, this one's easy to read too, 1,5-naphthalene disulfonic acid, cool, in 100 grams of H2O. So why don't you give it a try? Just to make things easier on you, the molar mass of that beautiful formula is 288 grams per mole. But try and follow the same rhythm. Find the molality first, multiply the molality by the Kb, find the delta T, add it to the original boiling point of water, come on back when you're done. Hopefully this is what you got. I kind of reduced steps a little bit here. I just kind of did the molality all at once over there on the left. So I took the grams I was given, I divided by the molar mass to give me moles, I divided that by the kilograms of solvent, multiply that by my Kb, I get 1.79. Again, that's not the answer, that's how much it increases by. I add that to the original boiling point of water, I get 101.79. Try one more. Be careful, this one's a little trickier because this time we are not dissolving in water. We are dissolving in a different solvent, nitrobenzene. But the approach is the same, 41.3 grams of 2-methyl-1-nitroanthraquinone in 1.00 times 10 to the second grams of nitrobenzene. Just to make life easier for you again, the molar mass of that awful thing is 267 grams per mole, of course. Give it a try. Same approach, just the Kb is going to be different this time. So go back and look at the table. It should tell you what the Kb is. Come on back when you're done. Now remember, in this situation, we weren't dealing with water here, so the Kb is different and the actual boiling point of nitrobenzene is different. So just make sure that that's something that you didn't get slipped up on. We multiply the molality by the Kb, add it to the original boiling point. So easy, I want to cry. Let's see if there's something that we can spice it up with a little bit. So let's continue to focus on boiling point, but sometimes when we're dealing with solutions that are ionic solutions, we have to consider that they are going to dissociate into their ions. There's some example problems in the book that kind of show this, but they kind of do things a little differently than we do it, so I want to show you the way that we do it. But all we do is we take our original equation and we just add a new thing that we call I. And I want you to think of I as in like the number of ions that a solution creates. What I really means, it's called the Van't Hoff factor, but you don't need to know about that. Let me just show you an example on how we calculate I. Let's say, for example, that we have nickel bromide, and we dissociate nickel bromide. So this is nickel 2 bromide. Our dissociation equation, that's Na, dummy, is going to be nickel and bromine like this. Now I want you to take a second and count the number of ions that we produced. This isn't very hard. I got 1 ion here, I got 2 ions there. So that means my I value for this particular equation is going to be 3. That's it, that's all it takes. So you just need to take one extra little step, count the number of ions that are produced in solution, and then just add that to your equation. Let me show you, it's really easy. So look at example number 10 here. So yours says calculate the boiling point of 21.6 grams of nickel sulfate in water and assume 100% ionization. So you could probably even handle this one yourself, but if you want to take a second and think about how nickel sulfate dissolves, just break apart the dissociation, and you should realize that it breaks apart into 2 ions, 1 nickel ion, 1 sulfate ion. So that means our Van't Hoff, or our I in this situation, is going to be 2. And then the rest you do the exact same way as we've done it before. Pause, come on back when you're done. All right, So hopefully this is all feeling very familiar at this point. The only difference here is that we have to include that I value. Again, it just breaks apart into two ions, so we just multiply that side of the equation by 2. You should get 101.44 degrees Celsius as the new boiling point. Now for number 2, I'm not going to go over specifically, but I would really like you to try this one on your own and then come back to me and let me know how you do about it. Just to make things easier on you, the molar mass of magnesium perchlorate is 222 grams per mole. And the answers that you should get, like I said, I'm not going to show the work on this one because I want you to try this on your own. But the answer that you should get is 2.68 degrees Celsius for the TB. And what you should find as your new boiling point then is 102.68 degrees Celsius. So don't just sit there like a lazy lemon. Try this problem on your own. It's there. Everything you need is in your notes. Give it a try and double check with my answers to see if you really got this. Make sure that you count out the number of ions appropriately because you will need to figure out the I value for the equation. And then that's it. And that's all. We're probably going to use these notes again, but we're going to circle back and do freezing point next time. So hopefully you left yourself a little room to do the freezing point problems. They're very similar, but we want to make sure that we do those as well. We'll see you next time.